Welcome to the Explainer. Today we are going to shrink a planet's entire core right down into a metal can. Seriously, it's all part of this incredible attempt to answer a massive question. What in the world powers that invisible shield protecting all life on Earth?
So before we dive into how they actually built this planet in a can, we've got to get our heads around the enormous mystery they were trying to solve in the first place.
And it is a huge question, right? How does a planet like Earth even get a magnetic field? I mean, we know the shield protects us from all sorts of nasty solar radiation, but what's down there acting like a giant magnet? The leading theory is something called the dynamo effect. But, and this is a big but, proving it is super hard. It's not like you can just, stick a probe into the Earth's core. So what do? Well, you got to build your own. And here it is. Say hello to the von Karman sodium experiment, or VKS for short. Okay, I know, it doesn't really look like a planet, but trust me, this cylinder filled with super hot liquid sodium is one of our best shots at recreating the very engine that powers a planet's magnetic field.
So the main idea here, the thing they're testing, is this dynamo effect. And honestly, the concept is pretty straightforward. You just take a fluid that can conduct electricity, think the liquid iron in Earth's core, or in this case, the liquid sodium, and then you just stir it up a lot. If you get the motion just right, it can take these tiny little magnetic flickers and amplify them into a massive, self-sustaining field. It's literally turning motion into magnetism. How cool is that? And the setup itself is it's genius. You've got this steel cylinder, right? It's filled with that liquid sodium. Then at each end, you have these two super powerful iron impellers, and they spin in opposite directions at insane speeds. This creates this incredibly turbulent, chaotic, swirling flow. And then the scientists just listen. They put probes on it and they wait, just waiting to see if this violent, metallic storm can actually create its own magnetic field from scratch.
At first, the experiment worked pretty much like you'd expect. But the really mind-blowing stuff, that started when the researchers decided to, mess with the machine's perfect balance. They decided to introduce a little controlled chaos. So first things first, let's establish a baseline. When both of those impellers are spinning at the exact same speed, you get this perfectly symmetrical flow. And it works. A strong, stable dynamo is born. The magnetic field just pops into existence and holds steady. That right there is the proof of concept. But nature is almost never that neat and tidy. Okay, this is where it gets really interesting. The researchers asked a pretty simple question. What happens to our dynamo if we break that perfect symmetry? What if one impeller spins just a tiny bit faster than the other? And that one simple change, it turned the entire experiment on its head. Now, to do this scientifically, you can't just eyeball it. So they created this single control parameter they called theta. Don't worry too much about the formula. Just think of it as an asymmetry knob. When that knob is set to 0, everything is perfectly balanced. But as you start to turn that knob, one impeller starts spinning faster than the other, and the whole flow gets more and more lopsided. So by carefully tweaking this asymmetry knob and just tracking what happened, the scientists basically created a map of all the magnetic possibilities. Every single point on this map is a unique flow condition, and as they started exploring it, they uncovered this whole range of bizarre, completely unexpected magnetic behaviors. And as they explored this map, they found something incredible. The magnetic field didn't just get, stronger or weaker. No, it developed a whole range of different personalities. It was like they discovered a whole zoo of different magnetic states. The first big surprise was finding two totally distinct, stable states. When things were close to perfectly symmetrical, they got what they called the stat high mode, a really powerful field, about 180 Gauss. To put that in perspective, that is way, way stronger than your average fridge magnet. But then, as they turned up the asymmetry, they found a completely different stable state, stat low, which was, get this, almost 10 times weaker. But what about the space between these two stable islands on their map? Oh, that's where things got truly wild. The nice, neat, steady magnetic field would just collapse, and in its place was a field that was constantly changing, pulsing, even flipping over entirely. So they started to catalog this magnetic zoo. You've got your two stable states, stat high and stat low,
Check. They also found spots where the field would just oscillate, swinging back and forth rhythmically, kind of like a pendulum. And then, and this is the really exciting part, they found settings that produced random reversals. The field's north and south poles would just spontaneously and unpredictably flip, which is exactly what Earth's own magnetic field has been doing for millions of years.
And they noticed something else really fascinating. As they turned that asymmetry knob, getting closer and closer to a tipping point between a stable state and one of these oscillating ones, the oscillations would get slower and slower and even slower.
This is a wild phenomenon known as period divergence. Just picture a pendulum swinging, right? But as you get closer to this critical point, each swing takes longer than the one before it, stretching out toward infinity until it just stops. In physics, that is a classic, textbook sign that a system is right on the edge of a huge change in its behavior. It's at a tipping point.
Okay, so now the scientists have this incredible collection of behaviors. You've got stable fields, you've got oscillations, random flips, these weird tipping points, and it's all coming from this one single machine. The next huge challenge was, how do you explain it? How do you find a simple rule that can make sense of all this beautiful chaos?
And that really is the central mystery here, isn't it? How can one tiny little tweak, just changing the speed of two propellers, unleash such a crazy variety of results? The answer, as it turned out, wasn't to look for something more complicated. It was to find a deeper, hidden simplicity. And the answer they found is just so elegant. It turns out this entire zoo of behaviors, all of that complexity, could be explained by the push and pull of just two fundamental magnetic modes, battling it out inside that liquid sodium. So the researchers built a model, and it showed that one magnetic mode was shaped pretty much like a simple bar magnet, that's a dipole. The other one was a little more complex, kind of like two bar magnets next to each other, a quadrupole. And when they turned that asymmetry knob, all they were really doing was changing the balance of power between these two competing shapes. And that constant competition was enough to create the whole shebang, the stable states, the oscillations, and even those chaotic Earth-like reversals. And that is the key insight here. It takes a wildly chaotic system and boils it down to a predictable, understandable dance between just two players. This VKS experiment is just a stunning reminder that all the huge, complex things we see out in the cosmos, from the shield protecting our own planet to the magnetic fields of distant stars, are often governed by these beautifully simple, underlying rules. It really shows that if we're clever enough, we can build these miniature universes right here in the lab, turn the knobs, and start to decode the very engine of the planets. What else could we figure out this way?